All right. Been away for a bit because I'm busy. I have a full-time job and stuff. But now I'm gonna do at least this one more video, and we're gonna talk about what a sampling distribution is, because this was one of the most confusing concepts to me when I was learning statistics. So, both as an undergraduate and the first few years as a graduate student, my professors would drop this phrase, the sampling distribution, from out of the blue as if everyone should know instantly what it is. And I'm sure it was defined, but when you first learn a word and it's defined once for you, it's not like you just know that word from then on, right? You have to hear it a few times and you have to hear it in context. And then maybe you know the word, or maybe if you don't know the word yet, being exposed to it like that does nothing for you whatsoever. It just doesn't activate any meaning inside your head, and you don't understand what this person is saying. Um, so yeah, in statistics classes, in my experience at least, they just rush through this concept and then assume everyone knows it forever after that. This video is an attempt to slow that process down a little bit, and explore this concept because it turns out that it turns up a lot in more advanced statistics. And it turns out that it's kind of important to understand sampling distributions in order to understand things like ANOVA, that's analysis of variance. So really what this is all about is prepping the way for some planned ANOVA videos. I should have gotten to these a long time ago, but I've just been, doing other things. But I'm going to get a series of ANOVA videos up so that we have that foundation, and this is kind of, setting the stage for that series. All right. So we're going to start as usual with a ridiculously simple example and then move on to more abstract examples. And in the end, you'll hopefully have a better grasp of what the sampling distribution is. The first thing to understand is that it's not just the sampling distribution, although we often use the phrase sampling distribution as a shorthand. It's actually the sampling distribution of a statistic. There's always a statistic involved. Most commonly, what you'll hear is the sampling distribution of the mean. But it can be any statistic, really. For example, you could have a sampling distribution of the variance, the sampling distribution of the skew, and so on. So what is the sampling distribution of a statistic? Well, it's all the possible values of the experiment, quote, take a sample and compute this statistic, end quote. So, roughly speaking, the frequency of each of those values. Now, I say roughly because for a continuous variable, it's more complicated. It's the height of a curve defined by an equation. But forget I said that for now. I only said it so I don't get bullied at the statistician's weekly Sudoku tournament. You don't need to understand that. You can just think of it now as the frequency of each possible value of a particular statistic given all the possible samples that I might possibly ever take out of a particular population. So let's do an example before we get too far into the weeds on that. And if you notice a similarity between the idea of a sampling distribution and a sample space, hold on to that idea because you're onto something. Anyway, we're going to start with the sampling distribution of the mean. And so imagine that the data that you're seeing right now on the screen represents the entire population of interest. So I told you this was going to be a ridiculously simple example. If you can't just see it right away, stop the video and calculate the population mean. So go ahead, I'll wait. It's 3, right? Hopefully you can just see it, but if not, go ahead and calculate it. So the population mean is 3 here. So let's do the experiment where we randomly sample 2 items from this population and calculate their mean. How many different ways might this turn out? Well, of course, just by chance, I might pick the 1 and the 2, right? And if I did, then the sample mean would be 1.5. Now, alternatively, just by chance, if I was randomly sampling out of this population, I might instead pick the 1 and the 3, in which case the mean would be 2. And if I continue this process and take all the possible samples of size 2 out of this population, here are all the possible outcomes, right? So all of these possible sample means are all the possible outcomes of our little experiment. Take a random sample of size 2 from this population. So that's the sample space of sampling 2 items randomly from a population of 5 with those particular values. Now to turn that into a sampling distribution, we just turn all those sample means into a frequency distribution, as if the means were data, which of course they are. So here they are, all the possible values for the mean. And now we need to turn it into a frequency distribution. So I have it all set up for you right here. Here's all the possible values that the sample mean could take in our experiment of sampling 2 out of that population of 5. And now we just need to count them up to create the frequency distribution. So how many 1.5s were there? Well, here's one right here. And I actually don't see any more of them. So there's only one 1.5. How about 2s? How many 2s are there? Well, I see one here, but I don't see any others, so there's actually just 1 2 as well. And if you keep doing that, of course, there's a 2.5 here and a 2.5 here, so there are 2 2.5s and so on. And here's all of them. You can pause the video if you want to and just confirm that I counted them correctly. But this is the frequency distribution for our experiment, and that makes it the sampling distribution of the mean for the experiment of randomly sampling 2 items out of that population of 5. Now, of course, the table is one way of representing the sampling distribution of the mean, but more commonly we want to draw a picture, and of course we're going to draw the frequency histogram. So this one is an ugly sampling distribution, but you can, even in this ridiculously simple sampling distribution, kind of see the hints of a curve here, right? You see that there are very few very large sample means, very few very small sample means, and most of our sample means are right around the population mean, right? We know in this case the population mean was 3. Now, of course, in a real data analysis situation, we don't know the population parameters typically. It's very rare that we would. If we knew the population parameters, we wouldn't need to sample. But just in general, we do know that our sample statistics should be around the population parameter value most of the time. Pretty close most of the time. It's going to be rare that we're very far away from the population parameter statistics if our sample is unbiased or at least not dramatically biased. Of course, I argue that in most situations, at least with human participants or human subjects as your subject of study, random sampling, and that's just a myth. I've talked about that in other videos. There is no list of an interesting human population that is so thorough that it's sufficient to say you've randomly sampled out of that population. But anyway, that's a different topic. I'm off topic here. I need to get back on. See, I write these things out and then I just get off topic. It's terrible. All right. So this is kind of an ugly distribution. Now, just for fun, we're going to repeat our experiment, except that this time we're going to take a sample of size 3 from this population and calculate the mean. I know, that sounds so exciting, right? And then we're going to kind of compare that to the sampling distribution of the mean when our sample size was just 2. And that's going to sort of teach us, hopefully, a little bit more about the sampling distribution of the mean, the sampling distribution of a statistic more generally, and why we like bigger samples more than small samples, and why you should always beware of small samples. So, of course, just by chance, now we're randomly sampling 3 items instead of just 2 from this same population we had before. So just by chance, I might get just the 1, the 2, and the 3, in which case my population mean, or my sample mean, my sample mean is 2. Of course, the population mean is still 3 here. And if I continue this and take all the possible samples of size 3, here are all the possible sample means that I might get. And so notice that the sample means are now bunched closer to the population mean, which, remember here again, was 3. So even when the sample estimate is wrong, it's closer to 3 than was the case for a sample of just 2 items. So for example, at the very most extremes, when we're sampling 3 items, the worst possible estimate of the population mean I can get with this sample of 3 instead of just 2 is 2 or 4. Whereas before, remember, our smallest sample mean was 1.5 and our biggest was 4.5. So you can see here that even our worst estimates are closer to the true population mean than they were when we were just sampling 2 items. So estimates get better in the sense of having less error with bigger samples. And of course, I've just illustrated it here with a single example, but that is true as a rule. Our estimates are going to get better the bigger our sample. All right. So hopefully you can see the resemblance between the frequency histogram of the example we just did. Now this is the frequency histogram of sampling 3 items, not just 2. And hopefully you can see the resemblance of that and the normal curve, also known as the normal distribution, also known as the normal probability density function, also known as the Gaussian curve or the Gaussian distribution. Man, this thing has a lot of names. Anyway, if instead of a population of 5 and a sample of 3, we had an infinite population and took an infinite number of samples, the sampling distribution of the mean would in fact be a normal curve. And that's guaranteed actually by something called the central limit theorem. Now I'm not going to go too into that right now. I'll do a separate video on central limit theorem all on its own. But the central limit theorem does guarantee that over the long run, which technically means an infinite number of samples, the sampling distribution of the mean is guaranteed to be the normal curve. And that's true even if the population itself is not normally distributed. So in other words, the underlying distribution of numbers that you're sampling from does not have to be normal. The sampling distribution of the mean will still be normal all over the long run. Now, of course, infinite samples are a fantasy. In real life, we don't get to take infinite samples. But it turns out that sampling distributions of the mean become practically normal, that is, not statistically detectably deviating from normal, at sample sizes typically around 30 or so, even when the underlying distribution is non-normal. Of course, it just depends on how not normal the population is distributed, but around 30 or so, around that sample size, the central limit theorem assures us that the sampling distribution of the mean will be really, really close to normal, if not perfectly normal. And of course, if you're sampling from a normal distribution, then the sampling distribution of the mean is normal at all sample sizes. All right, well, that's enough for now. Hopefully you were wondering about sampling distributions, and that's why you clicked on this video. And having wondered, hopefully now you have a better grasp of what those things are. You can do the same thing with the variance, the standard deviation, skew, kurtosis, really just about any statistic that you can calculate on data, on sample data. But more importantly, statistics like the t-test and the f-test are in fact sampling distributions for those statistics. So when you see those equations for the t-statistic or the f-statistic, the chi-square statistic, and so on, those equations are describing sampling distributions of those of the numbers that come out of those equations. So that's what the t-distribution is. That's what an f-distribution, a chi-square, all that stuff really is. Those are sampling distributions for what might seem like kind of arbitrary or bizarrely put together statistics, right? They don't make intuitive sense the same way the mean does, that you would put numbers together in this weird way from your sample. But the reason you put the numbers together in that weird way is because that describes a sampling distribution that we have known characteristics for, and that's how we turn them into inferential tests. All right, I'm rambling, so I will see you next time.